See, Sandra, Chering, Sharvari, Ricardo, Jasmine, Gillian, cameras back on. So you are now producing electronics. This week, we're going to do sensors, all sorts of inputs. Following week, we're going to do outputs, motors, displays. Then we're going to communicate between multiple processors, and then we're ready to build machines. So we're heading into a few weeks of electronics. And then we have an important recitation. I keep saying important recitation. They really are all important. But we have an important recitation on the 24th on machine building. And so one of the key goals of Fab Labs is Fab Labs making Fab Labs. So rapid prototyping of rapid prototyping. And so you'll be doing a machine building sprint, and the recitation is going to introduce you to how Fab Labs can make machines. Okay, so input devices. Um, and again, it's worse for some reason this year. Armando, Shoko, Sange, Chering, Sandra, cameras on in class. Maybe it's a pandemic habit of uh, joining videos in your pajamas, but this is a bidirectional class. So the assignment for this week is to measure something. And the linked assignment is Adrian, host of Saturday. For this week, rather than picking one sensor, he picked every sensor. So he has really fun examples of everything I'm going to show you for this week's assignment. So lots of sensors to cover. First, inputs. I've linked to a data sheet. This is a particularly interesting one for the AVR-DB family that has really good analog interfacing. But any of the data sheets are going to have the sections that cover all of the parts we're going to be using this week. There's the basic pins that we need to talk to. Then there's so the some of what we're doing are just going to be reading a pin, but the pin itself is a fairly complex system. Then we're going to be using the analog to digital converter and the comparator for making measurements. And you can't do this week's assignment just simply from software. You really need to understand what's going on in the hardware. So uh, let's see, if we get to the right part of the data sheet, um, uh, the analog comparator quickly compares two voltages, and then the analog to digital converter um, condition signals and then converts it to a digital value. And then we're also increasingly going to be using I2C. I2C, I'll talk more about in Networking Week. It's a digital interface to talk between processors. And increasingly, the sensors we're using can speak the I2C protocol. And so we'll talk to them not with analog, but with digital. So our first simple example is this is a button momentarily up, closed when you push it. This is a slide switch. And just a note about these before I go on, if you um, typically the way we use those is the button goes to ground. Inside the processor, you can turn on a pull-up resistor. And then if you look at the signal that comes in, it doesn't look like that. It looks like that. That over a few microseconds, it kind of rattles between being open and closed. And so debouncing is what you call dealing with the you could confuse this to say it got pushed and released quickly when in fact it's just rattling. So here's a Xiao C3 with a button and an LED. Um, in Arduino code, I have to tell it what pin I'm using. Um, I'm going to read an input with the pull up, and then I'm looking, is the button low, um, or is the button high? And then in Python, it's quite similar. I tell it what pin to use. I get them set up, and then I'm running a loop and I'm looking, is the button low or is the button high? And so with those examples, I'm going to reset the processor. I won't do all these steps for each example, but I'm telling it the Arduino IDE, which library to use. I have to tell it what board I'm on and what port I'm on, and then I can load my code. And now I push the button and the light blinks and I get a message. Then I'm going to do the same thing in MicroPython. So I have to load I'm going to reset the processor. I have to load Python. And you only have to do that once if you're switching from Arduino to Python. And now that it's loaded, I'm going to go into Thani as an environment. And I can run my Python code. And now I light the LED and I get messages and I can communicate. So here's the same thing with a SAMD11, which is an AVR processor that knows how to speak USB. And here's the same thing with the Tiny 412. And the Tiny 4, let's see, the SAMD we program over this JTAG interface. The Tiny 412 we program over the UPDI interface. And again, in this family of the AVR Tiny, you can get this in from small to many pins. And the fan club for this part in particular is it's 50 cents and it's a little 8-pin package. And if you just need to paste in a little bit of processing, you don't need all of the pins and power of the bigger processors. And so, and the code is essentially the same for each of these. Um, the Oh yeah, and a small difference here I show on the Tiny 412 using the Arduino serial library. In this version, what I show, and I'll talk more in networking week, here I'm doing the serial communication completely in software. So I'm not using a library. I'm using my own code to what's called bitbang to actually toggle pins to do serial. So all of that is just going through the processors and programming, which I won't go through now in detail. Now let's start sensing. So this is a sensor for magnetic fields. And so it puts out a voltage. Let's see, let's go back to um, let's see, let's look at this board. And so you give it ground and power, and it puts out a voltage, and then you have to read that voltage. And so to read the voltage, um, in the simple Arduino version, you just do an analog read. That hides a lot of the configuration of what the ADC can do. And uh, so what's happening now is I'm measuring the magnetic field and it's oriented. So if I flip it upside down, it goes in the other direction. And then here I'm going to do it with nothing. And if I flip it, you'll see a small change. And that's actually Earth's magnetic field. So it's sensitive enough to measure Earth's magnetic field. Um, so that's measuring magnetic field. And a killer app for this is if you want to find when a lid is closed or when an axis approaches an end stop. This is a common way to sense proximity of a magnet and a sensor. Jacob, the debouncing solution, um, the general solution, there are a few ways to do it, but the most common one is just a little time delay. This is on the order of microseconds, but the processor is faster than microseconds. And so when you first get a button event, you don't read it again right away. You have a little bit of delay before you read it again, is the most common way to debounce. Okay, so that's magnetic field. Then here's a great part that almost obsoletes what I just showed you. This is the same size package. It has a few more pins, but this is a vector magnetometer. So now on this board, um, here's our, I'm doing this on the 412. This is a header to the outside world. This part runs at 3 volts, not 5 volts. So I've got a regulator and a filter capacitor. I've got an extra capacitor on this vector magnetometer just to help. This is a bypass. It helps reduce electrical noise. And then I2C has 2 pins, SCL and SDA. One is clock, one is data, and they can go in either direction. And since they go in either direction, the way it works is you pull down with a pin and a resistor pulls up. So when you use I2C, you always have a pull-up resistor that goes to the power supply. So I've got my 2 pins coming in. And then if you look at the, let's see, we look at any shao pin out, for any of the parts we're using, um, there'll be labeled pins that know how to do SCL and SDA for I2C. So here are the labeled I2C pins. In addition, and I'll talk about this in networking week, you can do it in software. So what I have on the board is the vector magnetometer connected over I2C. And so it looks like this. And then here's what I can do with it. So I'm going to do this. Um, so let's see. First, just to explain this image, here's my project. Uh, I for the tiny 412, you program it over UPDI. And you can do that with a simple serial interface. So this is a UPDI programmer. And then on this side, I've got a serial port that converts TTL serial to USB, is why you see three boards. So I've now loaded my code, and you'll see it's measuring not just the magnetic field. I'll do all of this again. Um, so it's measuring not just the strength of the field, but it's measuring the position and the orientation. Okay, so that's a vector magnetometer. And so instead of just magnetic field strength, it has three magnetic field sensors, X, Y, Z. And so it gives you a strength and an orientation. And there are endless uses for that. You can use that to make, for example, a joystick. They're used, for example, in a shift lever that tells you what position the shift left lever is in. You can make a thumb wheel. You can make all sorts of interfaces by moving something around relative to something else and tracking the position of a magnetic field. So that's a vector magnetometer. Uh, this is a little potentiometer. And so that's a variable resistor. And I just show this here just in an example in another project. Here, what I'm doing is this is a motor controller, and I have to set a voltage for the motor current. And so this is a classic use where I have the potentiometer on a board, and just with a small screwdriver, I use that to adjust a setting that picks a voltage to control the motor controller. And we'll talk about motor controllers in a few weeks. Okay, now comes easily my favorite sensor. So, um, oh, let's see. This is a broken link for video. I'll have to fix that link. Again, this is why I keep repeating we need videos in the repo so the links don't break. Let's see. Hopefully this one is working. No, both of these are broken. Oh boy. Okay, I'll have to fix both of those links. Those are showing making touchpads. Um, uh, let's see. Adrian has examples of um, making a force sensor. And the broken links are both to measuring touchpads, like on your laptop. This is a link to how you use this sensing to measure bending. And you can use this to measure pressure, tilt, acceleration, humidity, proximity. And what's going on in all of these is uh, your uh, uh, um, a conductor. Inside your body, you're on the order of kiloohms of internal conductivity. And then outside you, there's ground in the room. And what we're going to do is we're going to have an electrode that puts out an electric field. It's going to flow through your body, and it either is going to go into ground or it's going to go into a receiving electrode. And so we're going to, these are very low voltages and currents. It's not remotely any biological, it's far from any biological effects. But what we're going to do is this is a circuit that emulates you. And then we're going to charge and discharge. So we're going to put charge on you and watch it reduce and put charge off. And then what I'm showing here is there are multiple ways we can do it. We can measure loading, we can charge and discharge, and we can transmit and receive. So this is circuit simulation on what I'm going to be showing in a lot of detail. So the first version is, this is nothing but a Shao SAMD11. Here's a ground and here's a series of electrodes. And it can do what's called Q-Touch. And then Adafruit has a free touch library where in hardware, the processor knows how to do this. So I set up pins to do capacitance sensing. And I start this running. And now what it can sense through a piece of paper. Now it's going to sense the proximity of my finger over those pads. So just one is a button. Now I'm tracking position. And then the ESP32 also knows how to do it. So here's a Shao, and this is doing MicroPython knows how to talk to that. So I set up pins as touchpads. And then with that, now I'm doing the same thing. I'm sensing my finger proximity to those pads. Then all of that, those are for processors that already know how to do that measurement, but you can do that on any processor. So what I'm going to show you next is I have a resistor going to ground and an electrode. Here I am. It's going to couple through me to the outside ground. And I'm going to first charge up. Then I'm going to switch this from an output to an input, and I'm going to listen to it charging down. So here, I've added these charging resistors, and now I don't need a special processor. I can do this on any pin, on any processor. So if I look at the code here, I'm going to, oh yeah, and I'm doing something else here. So first, let me show you what it does and then explain why this is a little non-trivial. So here's the same sort of thing. I'm sensing my finger's proximity. I'm doing this one on the RP2040. And remember, the RP2040 has what we PIOs. And sorry, I'm going to interrupt myself. Sanjivani, Ricardo, Sabaresh, Shomi, Chering. Cameras need to be on. The Shao has PIOs. It has these little processors around the main processor. And so in this example, I'm in MicroPython. I'm creating my own measurement peripherals. I'm creating a series of custom peripherals that can measure the step response. And then I read each one. And then what I'm doing here, and initially I don't expect you to understand this. This is the little bit of code that goes into the PIO processor that tells it how to make the measurement of the charging and discharging. And so here I'm building my own custom peripheral, and that then lets me read this on all of the pins to measure proximity. Now, this next version is I'm going to add a processor. And so here's why I'm doing that. When you make this measurement, this wire is sensitive. So if the processor's here, but the electrode is over here, you're going to be measuring everywhere the wire goes. And if you touch the wire, if it goes near something else, you'll get noise, you'll get interference. So if you have a processor here, but you need the electrode far away, what I'm going to show you is I'm going to put a little processor here to make the measurement, and then I'm going to send and receive digital signals. So in this example, I'm using the tiny 412 to make the measurement. And then right here, I could spread that out as far as I want because I'm sending digital signals. And then in this example, I'm doing it with bigger electrodes that'll let me see further away. So I can sense the proximity of my hand. And then it can sense the proximity of the book, and then I can actually sense through the book. So roughly the distance out you see is proportional to the size of the electrode. So now I'm using bigger electrodes and I'm sensing my proximity, my approach, not just my contact. And so um, uh, this is how digital calipers work. These are the electrodes inside of them. You can use this to, here I'm using this to make a linear sensor where I measure the capacitance between an input and an output. And so I'm just measuring capacitance between the inside and the outside. And when the dielectric comes in and out, I get a signal. So I'm using that to make a position sensor. Now, all of this so far is what's called self-capacitance, where I've got the electrode, here's the outside world, and then I'm using the room ground. And the problem with this will work different in different places because the room is different. So a better solution is you have a transmitter and then you have a receiver, and you measure what happens between the transmitter and the receiver. So in this version, what I'm doing is I've got two resistors. So I've got two transmitters on this board. I've got two receivers. On the receiver, I have a resistor up and a resistor down. And so now what I'm going to do is on the transmitter, I make steps like that here. And then on the receiver over here, what I see is little current pulses that look like that. And this is what I'm going to sense. Omar, what are you asking about isolation? Um, so here I've got two
You
transmitters,
mean,
two. Go ahead, Omar.
so I was wondering, like, did you mean using a transmitter and a receiver to isolate the
Sorry, Omar. Your
signal,
audio is
or
break.
like,
Sorry, Omar, your audio is breaking up. Can you type it in the chat? Um, So I've got two transmitters, two receivers. Um, they sense the object and then they sense my hand. And to understand what's happening, there's the transmitting electrode, there's the receiving electrode. There's an electric field between them. When I bring in the pad of paper, this has what's called a dielectric constant, and it pulls the field lines in. And so it's sensing the piece of paper. And then when my hand comes in, it's interacting with the field. So you can use that to sense a person. You can also use that to sense the proximity of objects. Then the same thing I described before, if here's my processor, if the transmitter is far away, that's fine, that's a high level signal, but the receiver is a low level signal. So in the next version, I'm going to put an amplifier over here and then send the amplified signal. So here I'm using this part that's a little powerful amplifier. And on the board, I've got the amplifier doing the measurement. And so this will look similar. So now it's sensing just the pad of paper, and then it's sensing me. But now I can separate the electrode far away and just send a high level signal. And then here it is sensing the book and then sensing me through the book. So with that measurement, you can make a button, but the button isn't mechanical. It's just a sensor. You can sense through a case. You can make a force sensor. You can make a slider knob. You can make a rotary knob by rotating capacitor plates. If you put a liquid in a tube, you can make a tilt sensor. If you put it around a container, you can measure a liquid level as the liquid comes in. If you make a rigid electrode and a flexible electrode, when you move it, you can measure their distance. And from that you can measure acceleration. If you make a curved electrode, when you rotate it, you can measure rotation. If you just have two fixed electrodes and you measure it sensitively by averaging multiple readings, you can measure the change in the moisture in the air and measure humidity. And not just that, this is my favorite app note. If you go up in frequency, so far what I'm describing is at low frequency. As you do this at higher frequency, you start to excite degrees of freedom within atoms. And then you can do all kinds of stuff. So this is showing, let's see, those were different alcohols. This is gin, vermouth, and a martini. This is frequency versus the signal. This is what are beer and light beer. This is wine after you open it. This is milk after you open it. Milk versus cream. You can actually get all kinds of physical chemistry information uh, uh, just by this measurement. Jacob, what is the video you're asking about? Are you asking about the class video? I do that within a day after class.
Okay, thank you. This was
Yeah.
my question.
Yeah. Frosty? No. Okay.
Yes, Neil, I find this really interesting. Our student is working on monitoring like a puffin hole. They dig a hole, so he wants to like count how often it goes in can this be used like outdoors? Can this like detect if it's in a tube or something like that?
Oh, sure.
Or
You can just, I mean, one of the great things about this as a sensor is it can be completely packaged. You know, you can isolate all of this, but what do you want to measure in the hole?
So like detecting if the puffin is going inside the hole and outside of the hole, and we can
Oh,
count how often
absolutely.
it
So
is
if you
going.
just have two electrodes, you'd see a big signal when the puffin goes through.
And is any one of those like op-amp, or should you try all of them, like these methods?
Let's see. I would do the transmit receive,
Yeah.
and depending on play with them.
Yeah.
The remote one is probably the best one because then you can have the electrode separate from the processor. But yeah, I'm sure you could get a good puffin signal this way.
Yeah. Thank you
Okay,
very much.
so all of that is step response. And what's so much fun about this is it's just arts and crafts. With just a vinyl cutter, you can cut out electrodes and make all sorts of custom sensors. Okay, next is here I'm going to measure temperature. So that's the temperature of my finger. And to measure temperature, I'm using a thermistor, which is a resistor whose resistance changes with temperature. And the trick here is to make what's called a bridge circuit. So we're going to have a variable resistor, and then you could put them with a fixed resistor and a voltage. But if we look at the voltage range, we'll be stuck in the middle. Instead, what we're going to do here is this goes to the supply. This is ground. Here's our thermistor. And then we're going to go into a differential amplifier. So what we're doing is normally these are balanced. The same signal goes on both sides, and we get zero out. And then when this resistance changes, instead of measuring a change in the middle of a range, what we do is we take a signal that varies relative to zero, and then we blow that up to the whole range. So just a divider like this, we only get a few bits of resolution. By putting it in a bridge, we get all of the resolution of our ADC. So the idea is you want to measure a small change in a small signal, not a small change in a big signal. So here I've got 4 resistors to make a bridge. And then remember going back to the data sheet, when you go into an analog to digital converter, you can measure a single voltage and get a number out. Or on most of our processors, you can put in a plus and a minus signal, and then what it puts out is the difference between those two. So it's a differential measurement. And then we measure the difference between those two voltages. So that's a thermometer. And then you can also get, oh, let's see, I'm not sure what happened to that link. You can get device. So your body makes what's called black body radiation. You emit light, but at a very long wavelength, infrared. And so you can get out, this is another link that's changed that I'll fix. You can get, when somebody points a non-contact thermometer to measure your temperature, it's measuring the spectrum of the light coming from you. And you can get little components that do that infrared temperature measurement. So that's how we do temperature. Then for light, we use photo transistors. So you can get ones that measure both infrared and visible. And this is a bipolar transistor. We use them with a pull-up resistor. And so light comes in and it varies the current that goes through here, which pulls current through the resistor that then varies the voltage coming out. And the size of the resistor controls the sensitivity. So here I've got my phototransistor and I've got my resistor, and I'm going to measure a voltage. And so you can see the shadow as I come by. Now, there is a problem with that, which is that's sensing me, but it would also change if like there's sunlight and an airplane flies by or a cloud comes over or somebody turns on and off the room light. So if you want to measure, for example, if you have a doorway, or let's take the puffin. If you wanted to measure a puffin passing by optically, you want to know the puffin crossing a light beam, but you don't want to know when the room light changes. So the trick here is what's called synchronous detection. So what I'm going to do is I'm going to have an LED putting out light. And then I'm going to have a phototransistor receiving the light. And it gets light from multiple directions. But I'm going to turn the transmitting light on and off. So if I look at my photodetector, there's a slowly varying signal, which is all of the light. It's night and day and clouds, whatever all the other light is. But on top of it is a high frequency signal, which is my modulation. And so I'm going to measure the difference between on and off. So I keep subtracting on versus off. And the difference between on and off is the light that came from here to here, and it gets rid of all of the light from all the other directions. So in the second example, I've got a LED putting light out, and I've got the photodetector coming in. And so what I'm showing here is this is the received signal with the LED on, received signal off, and then the difference. And so now what it's doing is it's measuring just the light that's bouncing off of me, and it's ignoring all of the other light. So that's a very powerful technique called synchronous detection. Okay. Now that was measuring all light. Now what I'm going to do is I'm going to measure the color of the light. So here I'm measuring light reflecting off of red, green, blue. So that's using a color light sensor. And so here's the sensor. And this is an example where you have to do reflow with paste underneath it. And then this is an I2C device. And so I'm connecting SCL and SDA. And then it's reporting to me digitally. I read it, and then I get the red, green, and blue values. So you can use that, for example, to sense the color of tags. You can do some basic spectroscopy to measure like the color of a material, of like skin or a leaf color. And then here's a really interesting, crazy variant. This is a part that's similar to that. It measures red, green, blue, and it also measures orientation. and it measures signal strength. And so this is designed optically to measure proximity. And it built into it, it tracks position, so it measures motion. So it measures gestures. And so you can do gesture control as well as sensing with that part. So all of that is light. Let's see, then here's a proximity detector. So in this video, it's down here at the bottom, and I'm trying to sneak up on it. So I'm moving, it says I'm moving, I'm not moving, I'm moving, not moving. So it's sensing me moving. This is a Doppler radar. And so it's not quite a radar, meaning it's not giving distance. Doppler means it's measuring the frequency shift. And these are cheap and cheerful. There's lots of clones that are identical, that these are just $1 or $2 each, and these can see many meters away. And so this is the best way to do proximity. You'll see you'll see these around. These are called pyroelectric. They measure the thermal radiation from your body. They're pretty much obsolete. The Doppler radars are much more sensitive and can see much further away. So that's a proximity sensor, but it's not distance. For distance, this is what we use. So right now I'm measuring distance in millimeters to the table. Then I'm going to turn it upside down, and I'm going to measure distance up to the ceiling. So now this is giving absolute distance, and this is a spectacular part. It makes a pulse of light, and it measures the time to return. Light travels a nanosecond per foot. And so to do that, it has to measure picoseconds. Incredible performance. And it can do that out to meters, but with tolerance of millimeters. Now, that's a small part to do reflow. So you can get these breakout modules for it, is what I'm using here. So I've got the breakout module connected, and then it's just an I2C interface to talk to the breakout module. And then in the code, I just do I2C communication, and I read the data back from it. I've got both Arduino and Python versions talking to it. Let's see, Marius, you want to make a 3D scanner. So there's a very interesting one of these parts that actually is a low resolution camera. It's just, I think this one is 8 by 8. This one gives you a little array. To build a 3D scanner, you would then need to move the object and move this. But note, so let me jump back to sonar modules like these are pretty much obsolete given the laser time of flight, but this is still a function of the surface. So you need to bounce light off of it. So really fuzzy surfaces will absorb the light, and really shiny surfaces will deflect it away. And so it would be easy to scan this to make a 3D scanner, and that would be a good final project, but it still would depend on the optical properties of reflecting off the material. So with making finer circuit boards and doing paste reflow, you can make your own. The part is only a few dollars. The breakout boards are higher. Let's see, for water depth, if it's a container, you can put electrodes around. You can do that with the step response. For water depth, that actually is a case where I would do sonar. So the laser optical won't have a good reflection from the top of the surface of the water. The ultrasound will have a very clear surface from the top of the water tank. And so for a big tank, I would use sonar. For a small one, I would do the step response. Here's a chip and a module with the chip that's very handy. This is a real-time clock. And so what this lets you do is right now it's telling me the time, but the time is wrong because I haven't yet set the time. So I'm going to run a program that loads the time into the clock. Then what I'm going to do is now just I'm not going to set the time, I'm going to ask the time. So I'm going to change the code so I don't set the time, it just reports the time. Okay. And now the key thing is I can unplug it and the little built-in battery keeps telling time. I come back and I plug it in and it's telling me the correct time of day. And so for things like a data logger, a clock, something that needs to know the time, this is much more accurate than just the timekeeping in the processor. Then, thanks to our friends in Shenzhen, these have come way down in cost. This is a GPS module. And so it's a simple I2C interface to the GPS module. And then what I'm showing here is for these sort of breakout boards, the way I do this with only one-sided milling is I mill the traces, I put pins through, I solder here, then I put the board on top of that and I solder there. So rather than having the pin go all the way through and solder on the bottom side, this lets me do one-sided milling but connect to a breakout board. And so here now I plug this in and it just starts, it first finds the satellites and it did it quickly because I had done that previously. And then it starts telling me my latitude, longitude, and it also tells me the time accurate to atomic clocks. So this works for GPS as long as you can see the satellites. It doesn't work, it works like in my house on the top floor, but it doesn't work on a lower floor. You need a good signal out to the sky. Okay, here's a popular series. This is an accelerometer, and it speaks I2C. And so there it is on my board. And with it, it measures the X, the Y, and the Z acceleration. So you can use that for gestures to sense interaction, sense motion. But even better than that is this is a borderline obsolete chip, but it's very common. You can buy it in these modules, and these modules are just a few dollars each. And what this has is three. So here I'm showing that same thing of how I do one-sided milling with a breakout board. This has three accelerometers and three rotational sensors. And what it gives me is roll, pitch, and yaw. So now I'm pitching. So you get AX, AY, AZ, and roll, pitch, yaw. Now, this is very subtle because physically you're getting rotation and acceleration, and then it's reducing rotation and acceleration. It's got yeah, Patrick, that's right. It's got 3 gyroscopes and 3 accelerometers. And so that's a 6-axis device. Then we get to the 9-axis device. And so here, I'm doing this with web serial. And I'm visualizing it. This is giving you roll, pitch, yaw. And this is the B&O 085 and a more recent one at 086. And this is subtle because the part is made by Bosch. This has 3 accelerometers, 3 gyros, and 3 magnetometers. And then there's another company that takes the Bosch part and then programs an embedded processor with their code to do the data reduction. So the reason for the 9 is the 3-axis gyro plus 3-axis acceleration. To get from rotation to orientation, you have to integrate, you have to add it up, and that drifts with time. So the magnetometer is there because the Earth's magnetic field doesn't drift. And so you use the gyro to measure rotation, the acceleration translation, and you use the magnetometer to anchor it from drifting. And so that's what the more complex software does in these modules. But these parts and modules cost $10 to $20 range instead of just a few dollar range for this. So for simple user interfaces, you can use the 6-axis, but if you want to anchor it, like it is a compass, but a 3-axis compass. If you want to anchor it, you use the 9-axis. Okay, that's motion. Now we're going to do sound. Okay, so I'm recording that sound. And so here, I2C is a digital protocol for interprocessor communication. I2S is a variant that's for audio, and there's both Arduino and I2C libraries. Almost always now, these parts have the audio port on the bottom to sense through the board, and that's because of how they're used in cell phones. You can do reflow, but Adafruit has a little module where they do the reflow for you, and it doesn't cost much more than the part itself. And then they have the pull-up resistors. So all I'm doing here is I'm connecting SEL and SDA. And there's no resistors on this board because they're on the Adafruit board. And it's this bottom port microphone. And then in Arduino, I can just do I2S. I have to tell it what pins I'm using, and I just read the audio samples. And then this is a little Python program to plot it. And that's all I need to do to record audio. This is a top port one, and this is now obsolete. The top port ones really aren't made anymore. But this is similar. This is now where I did the reflow instead of using a breakout board, and it does the same thing. I record the piano music. So we used to have to make much more complex circuits to interface to microphones, and you can still buy electret microphones. Those are all obsoleted by these MEMS microphones. So that's how you do audio. To measure force, this is a commercial version of that little video from Adrian. These are plates with a flexible material, and you measure the capacitance. You can get force sensing resistors, but yeah, force sensing resistors are a granular material, and the resistance depends on force, but they're poorly characterized. It has hysteresis. It's somewhat noisy. Let's see. The Benedict is asking about an acoustic camera. I have no idea what an acoustic camera is. Um, that's interesting. So it's a spatial imaging camera.
I just saw them a few weeks or days ago, and I was just curious if you'd
Yeah,
be able to explain,
yeah,
because I was a little bit confused. Is it just a sensor array, or how
yeah,
did they manage
right.
to match these two sensor data?
Yeah, my guess is they have a small array of microphones, and they're just doing time of arrival. So that they're mapping sound versus time and arrival in an array of microphones is my guess.
Okay, thank you very much.
Yep. So a strain gauge, let's see. A strain gauge looks like this, and you can make these in the lab. It's just a circuitous long wire. And the reason that's so useful is resistance is resistivity, a material property, times length over area. And so if you take a wire and you stretch it slightly, so if it gets longer and skinnier, you change the ratio of length over area. And so it's a long wire, and what you do is you attach that to a material, and when it bends, it stretches it a little bit, and you change the ratio of length to area. And so then you put that into to make a load cell. This is how you weigh yourself or you weigh a truck. You make a beam, and the beam bends under the load, and then you use a strain gauge to measure the bending of the beam. Let's see, there's a link to a YouTube on a sound camera. Yeah, it would be a good final project to make an array of microphones and use the time difference. Compared to light, time is much slower. Time delays are milliseconds, not picoseconds. And so you can very easily measure a time shift between a few microphones and localize where a sound is. Um, uh, oh, Load cells can measure weight arbitrarily accurately. This is how highest resolution scales work, because it's just calibrating the deformation of the beam. Um, um, let's see, there's a link in the chat about making your own sound camera. Yeah, this would make a good final project to make an array. Okay, angle, we use what's called a rotary encoder, reports out pulses versus angle. You can get MEMS chips that measure pressure. If you want to know your pulse, there are nice parts like this that measure the reflection of light, and from that they get blood oxygenation and heart rate. Um, these are sensors that measure pollution, air particle density of fine particles. These are kind of weird. These are sensors that measure gas, but they're not very specific. They're resistors that are functionalized with the material, and they respond to a lot of things. Now we get to a really important one, which is vision. So this is the sense module from Espressif. Sorry, not Espressif, from Seed. And so this is a camera connected to ESP, an Espressif shell processor in the Seed shell. So $14. And what I'm doing here is I'm going to start this running. And I've set it up as a web server. I could talk over serial, but I'm going to do this over the web. And so it's streaming video. And so there's the object. I'm inverting, I'm thresholding, and I'm motion detecting. So again, it's the object, the inverse, the threshold, and the motion detection. And then I'm streaming all of that over the web as video. So there's a lot going on in the code. I have to set up the camera. So yeah, all of this is setting up the camera. This part is streaming over the web. And then this is the interesting part. I get a frame from the camera. I convert it to data I can use. And then here I'm doing a loop. This is inverting it. This is thresholding it. And then that's motion detecting. So here I'm not using any libraries. I'm just, in the code itself, I'm doing the image processing. So I'm doing all of that at a very low level. Espressif has a library for their cameras. You can use a higher level library. And then Seed, now increasingly, there are these sort of modules that interface the camera to an embedded AI processor. And so these are designed built in to do things like recognize people, to do higher level applications. That's doing it all embedded. Then you can get webcams for just a few dollars and embedded Linux boards that talk to them. And then OpenCV is by far the most common vision library. And so in what I showed you, I'm doing all of the image processing myself in the code. OpenCV has all sorts of tools that'll let you do things like, say, find a face and track the features, or count the objects in a scene, or subtract the background, or track objects, or let's see, I should add a link. One of the things one of the great things you can, oh, I misspelled it. You can do with OpenCV is track Aruco markers, where this is a marker you can put in the scene. It's a little bit like a QR code. And then OpenCV knows how to find them, but track their position. So you can put Aruco markers on objects and then track how they move in the scene. So that's vision. And then WebRTC is how you do video on the web. And so in this example, what I'm showing is WebRTC can connect to a camera. And so now I'm doing everything I showed you on the Xiao, but now I'm doing it with a web browser that talks to a webcam. So once you reach the stage of having a computer that runs a browser, you can do all of this image processing right in the browser. And so in that example, I'm doing the same sort of code right in the JavaScript to do the image processing. And you can, there's a version of OpenCV designed for use in JavaScript. So that's lots of sensors. As a group, I want you to probe an input device. I want you to look at the analog and digital signals to understand what they look like. And then I want you to add a sensor to a board you've designed and read it. Let's see, later in the cycle, in this week, we'll talk about how to build user interfaces. Right now, Arduino or IDE or Thani have built-in plotters. You can use my Python code. For example, you can report out readings. Pick a sensor that relates to your final project. Adrian couldn't pick one, so he did all of them. And if you're not sure what to do, I encourage you to play with the step response, because out of all of these, this is the only sensor that doesn't need anything. All you need is a processor pin. And just with scissors or vinyl cutter and some copper, you can make all sorts of interesting interfaces, tracking all sorts of devices just with the step response. Okay, so by the end of this week, you should be comfortable getting signals into the processor and building inputs. Machine building recitation, open time as usual on Saturday, and then we'll go from inputs to outputs next week. Happy sensing. See you. Actually, I won't see you at the recitation. I'm going to be flying then. But happy measurement, and I'll see you all next week. Bye-bye.
Adios.
Bye.
Bye.
Adios, adios. Ciao.
Takk fyrir kærlega.
Peace.
Bye.